Hello, and welcome to Mastering Probability and Statistics in Python. If I say data science stands on the shoulders of probability and statistics, I might not be exaggerating. That's true. All the recent advancements in data science and machine learning, they can be traced back to the fundamental concepts of probability and statistics. Even some statisticians say that the data science and all its recent advancements, they can be just modeled as a branch of statistics. The importance of the subject can be realized by the fact that, for example, consider an example of a deep neural network that is being trained for months and months on petabytes of data, very large amount of data. But after all that training, at the end of the day, the result of the training is a probability model. So all that effort of months on petabytes of data actually come up with a probability law. I mean, you learn a probability law. So yeah, I mean, this is extremely important subject, particularly for data science and advancements in data science. So let's dive in. Let's dive in by focusing on the very basics and very fundamentals of the subject. So we start with the question, what is probability? Well, probability as a theory deals with predicting the confidence or likelihood for future events, something that is going to happen, how likely it is that it is going to happen. And probability as a number is basically that number is modeled between 0 and 1. 0 and 1. 0 means something that we are curious about. If the probability is regarded as 0, that means it is not going to happen for sure. And if the probability is regarded as 1, then that means the event that we are curious about will happen for sure. And any number in between, for example, 0.73 means we are 73% confident that the event will happen. So probability as a theory, it deals with the rules and laws of rules and laws and all these kind of mathematical derivations that deals with predicting the confidence or likelihood for future events. But probability as a number is that confidence value for the future events. Statistics, on the other hand, involves the analysis of frequency of the past events. So it is good to notice the difference between probability and statistics, although they work in common, and most of the time the terms are used interchangeably. But it is good to notice the difference between the two. If I say that in probability theory, we need laws that help us predicting the future. So we need certain laws or rules that are required to draw predictions in the future. Then statistics, the goal of statistics is to come up with those rules from the data. So statistics actually draw rules from the data that is available, historical data, the data that is available to date. It analyzes the data, maybe visualizations of the data, all different sorts of analysis on the data, and somehow come up with the rules that governs the pattern and the laws. And once the rules and laws are available, the task of probability or the probability theory or the probabilist, the task of that is to get those rules and make the predictions about different kind of events in the future. So you can think about the difference between probability and statistics in the following timeline way. So think about that's the time that's the time that is going on, And here at this particular stage we are sitting. So let's say we are sitting right here. And this is all the data that is available. And these are all the events that happen in the past. And right now we are here. And we want to predict what happened next. For example, we want to predict the likelihood or the confidence of something that can happen at this particular time interval right now here. And right now we are sitting here and we want to predict what is going to happen here. Now, sitting here, the task of a statistician is to look back to the data and come up with the rules and laws and patterns that can help for making predictions in future. Once you go back and see all the data, you analyze a lot of data, you apply all kind of artistic skills and scientific skills, whatever you want to, but you come up with the rules. Once the rules are available by looking backward to the data, now the task of probability or probabilist is to look forward and use these rules and make predictions. Obviously, if we have more data, if we can come more data, if we reach, for example, at this point in the timeline, we might have more data, and a statistician may go back and refine the rules if the rules are refinable. But the distinction here can be made in a way that you look back to the data and come up with the laws and rules and patterns. And then using those laws, rules, or patterns, you look forward in the future and make predictions. So looking backward is what the statistics is about. Looking forward in future is what the probability is about. So it is good to notice this distinction. But in practice, the terms probability and statistics normally used interchangeably, or sometimes people just use the term statistics, although it is good to notice the difference between probability and statistics. People even say probability is pure mathematics and statistics is like an art. I mean, there are a lot of phrases out there. So yeah. Next we see what sets are. You might be thinking, well, why directly from probability to sets? Well, I would say probability theory, it uses the set theory extensively. I mean, it uses the set extensively to build all these kind of data structures and structures to make predictions and stuff like so. So it is good to just get comfortable with what a set is. Set, in a very layman terms, is a collection. It is a collection. First of all, it's a collection. Like you have so many collections at home maybe, or in your office or something like so. A bookshelf, for example, is a collection of books. Your bag that contains maybe your laptop, maybe the charger or the batteries of the laptop, or maybe some books or notes or stuff like so, that is also a collection. So set at the end of the day is a collection. But not every collection satisfies to be qualified to be called as a set. A collection that has two properties, property one is the collection must be unordered. Let me write that. The collection must be unordered, which means in the collection there should not be positioning of different objects. So you have collection, you have different objects. Which object is at which position in your collection? If that is not a matter, then we will say the collection is really unordered. There is no positioning of different objects inside the collection, or shuffling the objects here and there does not change the collection. If that's the case, then we will say the collection is unordered. The elements of the collection, they have not positions, designated positions inside the collection. So one property of the collection is unordered. The other property is They must all be unique or distinct. There shouldn't be any copy of the object. So if I define the set, it's a collection, let me write unordered collection of distinct objects. Here we need to focus on some words: collection, unordered, distinct, and objects. Objects can be any objects. I mean, they can be books, they can be, any objects in the collection. So as long as you have a collection and it is unordered, all the objects, they are unique, there is no object having copy in the collection, we call that collection as a set. Normally in mathematics, the set are written in these curly braces that represent a collection. For example, this is a collection and this is a set, and it is always good to denote set with, rename the set with some nickname, so that whenever you want to refer the sets again and again, you can refer the sets with their names. And about the objects inside the set, they can be any objects. I mean, they can be numbers, strings, tuples, they can be other sets inside the sets. All these things, I mean, this 1, 2, 3, they're called members of the set. And for example, 1 belongs to this set. However, 5 does not belong to the set. So a set can have any kind of members, any mixture type of members, no matter what. However, a common practice is to keep the sets of same kind of objects where the similarity is defined in certain way. Keep those kind of objects in different kind of sets. For example, set of numbers, set of strings, set of locations. These might be different sets, or maybe you dump all the numbers, all the locations, and all the strings or names inside one set. That is allowed, as long as it's an object that have some definition. You can just include that object inside the set as a member. And again, the set can has other sets as members, because there is no restriction on the object that is there inside the collection. So this should be noted. Next, we talk about some operations on the sets. What kind of operations that we can perform on the set? There are a lot of operations. Let me list a few of those. For example, union of two sets. Union operation, let's say we have set A, 1, 2, 3, 4. And let's say we have set B, which is, let's say 3, 5, 4, maybe 1. Let's say we have these two sets and we take their union. So the union is normally written as A union B with this U symbol. And the union is just the union of the two sets. That's just you combine the two sets together, but because the definition of the set does not allow the duplicates, you just represent all the values that occur in both of the sets just once in the resultant set. So for example, 1, 2, 3. 3 does not occur twice, although when you combine set A and B, 3 should appear twice. But in the resultant set, because the result is also a set, and set cannot contain duplicates, so this 3 will not appear twice. Similarly, this 4 will not appear twice, and this 1 will not appear twice, and then this 5. Now you can see in A union B, this is a set. Both B and A, they are subsets of this set. A subset is just a set that contains all the elements of the parent sets. So we can say A is a subset of A union B, which means all the elements of A, they are also there in A union B. Similarly, B is also a subset of A union B, which means all the elements of B, they are also there in A union B. So that's what a subset is. Because we talked about subset now, it is good to talk about an empty set. If we have, for example, a set 1, 2, 3, 4, then this particular set, for example 2, 4, that's a subset of A because all the elements of this set, they are also present in A. And there is no element of this set that is not present in A, so this is called the subset. About the subsets, empty set is also a subset of every set. That's by definition. People define empty set to be a subset of every set. And further, the set itself is subset of, every set is subset of itself. That is also a definition. These two things are a little more, these two things are, these may be confusing, but it is good to note that empty set is defined to be a subset of every set, and a set is subset of itself. Even sometimes equality between two sets is established, like if A is a subset of B and B is also a subset of A, if these two things happen at once, that means A and B, they are equal. So sometimes the equality in set that is also defined like using the subset operations. Yeah, so there are a couple of more operations. Let me move on to the operations one by one. There is another operation called intersection. Intersection. If you have set A, let's say 1, 2, 3, and 4, and you have set B, let's say 2, 4, 9, then the intersection of two sets written in this form is just the common elements between two sets. What are the elements that are common to both of the sets? In this case, 2 and 4. This is common to both A and B. It is also important to note that A intersection B is always a subset of A, and A intersection B is always a subset of B. Even if the intersection is empty, even if A and B, they both have no element at all that is common, then the intersection will be an empty set. And because empty set is a subset of every set, so these kind of rules, they hold for empty set as well. One more thing about empty set, sometimes this empty set is also denoted by this kind of symbol. But it is worth to mention that if a set contains this empty set as an element, this set is no longer empty because it has an element, and that element has a particular definition. The definition of this element is it is an empty set. So that's an object inside this set. So this set is no longer empty, although this set is an empty set, and this is also an empty set. So these kind of distinctions should be noticed. Other than intersection and union, we have difference, A minus B. Normally this A minus B is written as, the set difference is written as with this kind of this kind of slash, but it is okay to write minus as well, although this minus is more common notation. This slash is more common notation in sets. So whether you write A minus B or A slash B, that means the set difference. The difference between two sets, A and B, so A minus B is the elements of A that are not present in B. So for example, take an example of set A and set B here, and we say A minus B is all the elements of A. So A minus B is just a set of elements of A, but those elements that are not in B. So for example, the element 1 is not in B, so we list that in A minus B. Element 2 is in B, so we will avoid this element. Element 3 is not in B, so we will write that. Element 4 is also in B, so we will not write that element. So A minus B is all the elements of A that are not in B. Similarly, B minus A is all the elements of B that are not in A. In this particular example, B minus A would be 9 because the elements of B that are not in A, that is simply 9. Another thing that appears from this set difference is sometimes we denote one particular kind of set as universal set. sometimes denoted as omega. Universal set is a set that is assumed to be a set that all the sets that are of our interest, they are subsets of universal set. Each and every element that is the element of interest that belongs to universal set. And all the sets that we are talking about, they are subsets of universal sets. So you can think the universal set as containing the whole universe, and everything in between the universe are substructures that we might be talking about. If universal set, for example, here, let me define the universal set to be, just in case we are talking about just the elements, just the numbers from 1 to 10, let's say that's whole our universe. We talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that's our universe. All the sets, they are subsets of this, and that's our domain we are working in. Then a complement can be defined as simply as a set difference, all the elements of the universe that are not in A. So that's a complement. Similarly, we can define complement of any set that is the difference from universal set to that particular set. So that's the complement. Further, we can define, just in a connection of intersection, we can define disjoint sets. Disjoint sets, the two sets are called disjoint if their intersection is empty. If there's nothing in common, then the sets are called disjoint. And the definition of this disjoint sets can be extended to multiple sets as well. Another related concept is partition. A partition is basically, so let's say we have a set S, and we have some of its subsets, let's say S1, S2, and S3. Let's say we have a set S, and we have other sets S1, S2, and S3. We want to see whether S1, S2, S3, they form a partition of S or not. Well, forming a partition of S means all the sets S1, S2, and S3, first of all, they must all be subset of this S, and second, their union must be the parent set S, and third, there should be nothing in common. So S1 intersection S2 is empty, S1 intersection S3 is empty, and S2 intersection S3 is also empty. So if you have subsets that are all disjoint and their union is the parent set, and in that case we will say these sets, they form a partition of this particular set. Now, coming back to complements, there are certain beautiful kind of laws by De Morgan that I should mention here, that if you have A union B, if you have two sets and you take their union and then you take complement of the union, that is equivalent to A complement intersection B complement. That's one De Morgan law. The other De Morgan law just flips this union and intersection from left hand side to right hand side, and that works. So yeah, so these are kind of very basic kind of operations in the set. We will be seeing the operations and the definition of the sets in Python as well. So let's go to Python and just get comfortable with the definition of set, what the sets are, what the subsets are, and let's get comfortable with the operations on the set in Python.